So we're now on the notes page 13, continuing with Lewis dot structures. Start out by having you draw what's called xenon tetrafluoride. A couple of interesting things happen here. When you add up your electrons, you end up with 36 valence electrons. So you start to draw your molecule. Xenon, stick fluorine off of it 4 times. Of the 36, we've used 8, so we have 28. Xenon already has an octet. Fluorine, each fluorine needs 6 more, so 1, 2, 3, 4, 5, 6, 12, 18, 24. Likely have never had this problem before. If anything, you run out of electrons and you have to make double and triple bonds. But in this case, we have extra. Well, it turns out xenon is such a big atom that even after it attaches these 4 fluorines, it still can have extra electrons. So the extra 4 go on the xenon. And so the xenon actually has 12 valence electrons, and that is called an expanded octet. So anytime you have extra electrons or too many electrons, give everybody their octet and then put the extra electrons on the center atom, which will usually be a fairly large atom. Another example I have here is sulfur hexafluoride, SF6, unit with 48. Turns out the sulfur goes in the middle and then it ends up with 6 single bonds, each to a fluorine. Now this molecule has an interesting use. It's a gas, but it's a fairly heavy gas. And so, for example, if you pause this and you go and search YouTube for sulfur hexafluoride, you'll see some videos where people inhale it and it does the opposite of helium. Helium, of course, as pretty much everyone knows, will make your voice higher, but sulfur hexafluoride actually makes your voice lower. And you're welcome to do that. If you want to try it yourself, to purchase sulfur hexafluoride is a little bit expensive, but the bigger problem is it's really bad for the environment. So it's not the best thing to purchase it and experiment with your voice, because all that sulfur hexafluoride is going to be let out into the environment and it's not good for it. So that's why I've never done an actual demonstration with it, especially since they're already on YouTube. All right, another thing you might have noticed is you might have thought, wait a second, xenon is a noble gas. What the heck is xenon doing bonding? Well, when you look at the periodic table, the first few noble gases like helium, neon, and argon, they don't really bond. They're so satisfied and their situation is such a low energy situation, they don't really bond. But all the other noble gases under them, like xenon, actually can bond. And part of it is because their valence electrons are so far away from the nucleus that you have more possibilities than you would with the smaller atoms. Moving along, we get to hybrids. Now, a hybrid is anytime you mix something. The popular thing right now are hybrid cars. And so a hybrid car is a mixture of a gasoline-powered and an electrically powered car. There's a bunch of different berries that are hybrids of other berries being mixed. You can think of yourself as a hybrid of your parents. But in our case, we're going to look at the mixing of orbitals. And as I mentioned in an earlier lesson, it always is trying to get lower energy. So the first one, sp, if you take beryllium, typically you would end beryllium with an S with 2 electrons. But it turns out what it can do is one of these electrons, I'll take this one, can jump to the p orbital. And because we're mixing an S and a single p, it is referred to as an sp hybrid. The orbitals are considered as having been mixed. And what this leads to is a lower energy situation for the beryllium. And it also helps explain why beryllium can make a molecule with 2 single bonds. And that's it. Beryllium is special. It can actually be satisfied with 4 valence electrons. So a very unusual situation. And now going on to boron, a similar thing happens with the boron, in which it can hybridize by taking this electron and sending it here. We've now used an S, a P, and another P, so that is known as sp2 hybrid. And it allows it to make 3 single bonds, and that's why boron, you might see a molecule in which it has 3 single bonds and no unshared pairs. So it's okay with 6 valence electrons. So again, a special situation. sp3 is the one you really need to know. This is the special one. This is the one that happens a lot. And this is what I call the wild card of hybrids. If you're ever given a hybrid question and you don't know what to do, your best guess is sp3, because it's what carbon does, and as carbon-based life forms, that's important to us. What happens is this electron jumps over here, and you're left with an S and 3 P's, each with a single electron. And because you combine an S and 3 P's, we can call them PX, PY, and PZ. That's why it's known as an sp3 hybrid, because that's what's been mixed. And again, as I say, like always, why? Low energy. They can get a little more exotic. In this situation, sp3d, phosphorus can do this. I sent this electron over here to an empty d orbital. And because it's an S, 3 P's and a D, sp3d. Here, sp3d2, sulfur can do this. In this case, 2 electrons jump. This one I jumped here, and this one I jumped over here. And so now we've combined an S, 3 P's, and 2 D's, so sp3d2. And this helps explain that molecule we drew above, the sulfur hexafluoride. It makes sense because if you have S and 3 P's and 2 D's each with a single electron, that gives us the ability to make 1, 2, 3, 4, 5, 6 single bonds. And that helps explain the existence of sulfur hexafluoride. A problem can come up that'll really trick you, like what I have here. When hybrids happen, you have to be in the same shell. So for example, what's happening here in this sulfur hexafluoride is this is all in the same shell, every one of these. So this situation PCl5 is an sp3d, and it exists. NCl5 cannot exist. Well, if you take a look at nitrogen, nitrogen will have a 2s and a 2p, like so. But there's no such thing as a 2d to jump into. So trying to take this electron and send it into a 2d is not possible, and that's why this cannot exist. Now let me check my nitrogen there. I think I might have the wrong orbital notation on that. I don't have a periodic table with me. Oh yeah, I knew that felt wrong. It should have 3. It should actually be like this. I knew that felt wrong. It still doesn't affect the result here. Now I have this little diagram that shows with pictures what it looks like when you make a hybrid. In this case, this is an sp hybrid, and it combines an s and a px orbital, and it changes the shape of where the electrons reside. And you end up with this situation here, and when you combine it, it combines to look like that. You might say, well, it looks similar to the peanut over here, but it's a slightly different version. And that's just a 3D image of what it looks like. All right, moving along. In the cases I've done so far, electrons have said to have been promoted. I promoted an electron from the s orbital to a p or a d. But every covalent bond is considered a hybrid because it's being shared with other orbitals. So take CH4, methane. What happens here, if we focus on the center atom, and I'm only looking at carbon right now, this carbon's electron configuration would typically be 2s2, 2p2. But when this electron jumps over here, you then get this, and it's going to form 4 single bonds, 1 to each hydrogen, in which each of these is considered an sp3 hybrid. And so anytime you have a covalent bond, that's also a hybrid. And the way you determine what the hybridization is on the center atom, and normally you're asked for the center atom, is you count every bond as one hybrid. You don't count the extra electrons in the double and the triple bond. So if you make a single bond, that's a hybrid, but then the double does not count as a hybrid and the triple does not add to that. So what I often say is count the number of thingies on the center atom. So if you take this example here, the xenon has 6 thingies on it. And each thingy, that's not what I meant to do. I meant to do this. Each thingy counts as one part of the hybrid. So I've got an unshared pair, that's 1, a bond 2, a bond 3, an unshared pair 4, a bond 5, and a bond 6. And so you just go in order. S is 1, 2, sp2, sp3. I've now done 4 things. That's 5. Another D gives me that. Those are 6 things. I've got an S, 3 Ps, and 2 Ds. sp3d2 is 6 thingies. Taking a look at ammonia, it has 1, 2, 3, 4 thingies, sp3. If we look at the carbonate polyatomic ion, it has 1, 2, 3 thingies. And again, the double bond only counts as 1 thingy. So that's why it's sp2. The extra electrons in the double bond are not hybridized. And this is just extra. It kind of follows the same pattern, and we don't really need to spend any extra time on that.